we're going to do spring mass system. So consider a weight. So I've got a weight here hanging on a spring, and there's forces on it. Now remember Newton's second law. Newton's second law was that the force is equal to the change in momentum, or momentum is what? Mass times velocity. We would better know it as F equals ma. The force is equal to the mass times acceleration. And that force that we're talking about, the force that's equal to ma, that's the resultant force. So that's the force we see, the sum of all the forces acting on the object. So if the object is the mass hanging on this spring, then what forces do we have? Well, we have gravity that's pulling down, and we have the spring. Oh, we got to do the law for the spring, Hooke's law. Now Hooke's law says that the force of the spring is proportional to the distance stretched. So let's look at the forces on this particular mass. We've got gravity pulling down. So here's where I've got this F equals ma, and the forces are the resultants of gravity pulling down, and the spring is proportional to the amount stretched. If, oh, we gotta, how are we measuring this? What's y? Y is going to be the distance that the spring is stretched. So if it's not stretched at all, then it's 0. The y is 0. There's Hooke's law then. If it's below the center of oscillation, I mean the mass is oscillating up and down. If the mass is below, then the y is pulling upwards. And if the mass is above, so in other words the spring, it would be compressed and would be pushing downwards, then yeah, the spring is always pushing sort of opposite where we are in comparison to the zero of our coordinate system. So right now we're measuring y as the distance that the spring is stretched from its unstretched length. So this here, mass not moving, that still has a positive y. We know that when this oscillates around, it oscillates, it goes above the equilibrium, below the equilibrium. But right now we're measuring y and as the distance that the spring is stretched. So we've got our F equals ma, and that's the resultant force. We've summed the forces on it, gravity and the spring constant. Since the acceleration, well, y is a distance, so change in y with respect to time would be velocity. That'd be the first derivative. The second derivative would be the change in velocity with respect to time, or y prime prime, the second derivative. So now I'm eventually going to end up making a linear second order constant coefficient differential equation. That's where we're going with this. So now I've got my model equation, and it's a solvable equation. If I bring this over, I've got, well, it's linear second order. I can write this as sort of a more familiar my prime prime plus k times y is equal to minus mg, is equal to a constant. So let's look at this. It's linear second order constant coefficient non-homogeneous differential equations. A differential equation. We can totally solve this. We get the eigenvalues. Well, how would we get the eigenvalues? Our auxiliary equation would be m lambda squared plus k equals 0, and our eigenvalues then would be equal to, we get complex conjugate eigenvalues with 0 real part. We'd get our eigenvalues of root k over m I, purely imaginary eigenvalues. And we know how to solve this. Our solutions would then be equal to, oh, we know how to get our homogeneous solution. Our homogeneous solution would be y homogeneous is equal to we'd have some constant sine. Now, I keep having to put this root thing in. That's why in physics they just call the root k over n, they call that omega, so that they can just write, they can write sine omega t plus c2 cos omega t. We're gonna not write that, but we could. So this would be our homogeneous solution to that linear second order constant coefficient differential equation. Now we would what? We need to get a particular solution. We know two different ways to get the particular solution: variation of parameters or unknown coefficients. We would use unknown coefficients in this case because the target function is just a constant. But we can make the, we fully solve this. Oh, there are two constants. How do we get the constants? Initial conditions. How could we have initial conditions? We'd have two initial conditions. You'd have to tell me where the mass was located originally. That would be y naught. And you'd have to tell me how fast it was going originally. That would be y prime naught. We'd have two initial conditions to solve for those two constants. Of course, we wouldn't solve for those two constants yet. We'd have to get the general solution. We'd have to add the particular solution to this homogeneous solution. So there's still a bit more work to do. Instead of doing that, though, I'm going to change my coordinate system. I'm going to change how I'm measuring. Instead of measuring from the length of the unstretched spring, I'm going to measure from equilibrium instead. Now, what is equilibrium? Well, equilibrium means no change. At equilibrium, y prime should be equal to 0 because it's not moving, and y prime would be velocity. If y prime was equal to 0, then y prime prime would be equal to 0. So we can go right back up to our model equation, set y prime prime equal to 0, and solve for the equilibrium. We get the equilibrium value of minus m over k times g. That's the equilibrium value. That's where we're oscillating around. If we set the spring right equal to the stretched length of minus m k over g, then it doesn't move. It's at equilibrium. So what I'm going to do then is a coordinate shift. I'm going to remeasure. Instead of measuring from the unstretched spring, I'm just going to measure from the center of oscillation. So I'm going to call, instead of measuring in x, I'm going to measure in y. What's x? Well, here's my coordinate shift. X is equal to y minus the equilibria point. So, and I know what the equilibria point is, so the x coordinate is equal to the y coordinate plus mg over, mg over k. Notice that if I differentiate x, x prime is equal to y prime, because this piece is a constant. X prime prime is equal to y prime prime, again, because this piece is a constant. When I do that, let's go back to my model. Here's my model equation. So I'm replacing y prime prime with xy prime, and I'm replacing y with, well, if x is equal to y plus the equilibria, then we can say that y is equal to x minus the equilibria. So I'm going to replace this y with its version in x. And now when I clean this up, you'll see that this minus mg cancels with this minus mg, multiply the k through, and my new equation is mx prime prime plus k times x equals 0. So by measuring from a different, in a different coordinate system, by measuring distance from a different spot, essentially, I end up with a homogeneous equation. Now, look at this homogeneous equation. It's just x's swapped out for y's. So the auxiliary equation is going to be exactly the same. The eigenvalues are going to be exactly the same. But our bonus is that our solution to this equation, then there is only the homogeneous solution, so that's the general solution. This is our solution to simple harmonic motion. Simple harmonic motion represented by, I've got the mass times the second derivative of position plus the spring constant times the position. We also remember that we can write it in one, we can write this in one shifted sign function if we want. So what did we say here? Plus phi. So it's a second order. We get two conditions. Those two initial conditions would help us find the two constants, either C1 or C2, or A and phi. So this is our example of simple harmonic motion. There's really only two parameters. What's the mass and what's the spring constant? Oh, then because it's oscillating, we can ask what's the period. Well, we know that period is equal to 2 pi divided by the imaginary part of the eigenvalue. So the period is equal to 2 pi divided by the eigenvalue. Divided by the imaginary part of the eigenvalue. It's all imaginary part in this case. So 2 pi divided by, there's the formula for the period of oscillation for our simple harmonic motion. Let's do an example. We got a 1 kilogram mass. Already they told me what m is. I know half the parameter. Is on a spring and it stretches 10 centimeters at rest. Let's do everything in regular metric units. So this stretches 10 centimeters. I'm going to read that as 0.1 meters. The mass is further pulled down a further 5 centimeters and released. Employ the above model. Alright, so the above model is here, because I'm going to choose to measure distance from equilibrium. So I have a homogeneous second order linear constant coefficient differential equation. We know the mass is 1, so I'm replacing that with a 1. I don't know what the spring constant is yet. Oh, but they give me the mass is placed on a spring and it stretches a further 0.1 meters. So they're telling me that the equilibrium is 0.1 meters. So we knew the equilibrium value is 0.1 meter. We know that the mass of the object is 1 and stretched down, so I'm just going to get rid of the minus sign. We know that G on Earth is 9.8, and that's going to let me figure out that K is equal to 98. So now I have the whole equation. Now I could look at it right now as, now I've got a linear second order constant coefficient differential equation, and I can solve via the normal way, but I sort of already know what the solution is. I know the solution. I'm just going to grab this one here. I know that K is 98 and M is 1. So I also know that the period is 2 pi divided by root 98. Oh, I just need to know the constants. How do I get the constants? Initial conditions. What are the initial conditions? Well, the mass is pulled down a further, so down from equilibrium. So x naught is equal to minus 0.05, and I need x prime naught. Well, it says it's just released, so its initial velocity is 0. Here's my initial conditions that I'm going to use to sub in and find my constants. When t is equal to 0, x is equal to minus 0.05. So since we're doing this in x's, these should all be x's here. Let's go back up here. Right, because that's the the general solution and the homogeneous solution, but in terms of x. If I really wanted it to be y, I'd go back up to here, and y is just equal to x coordinate shift. So when I make t equal to 0, I get sine is 0, that's going to be 0. Cos is 0, that's going to be 1. So it looks like C2 must be equal to minus 0.05. So now our equation is, I know that C2 is equal to minus 0.05. All right, I need the derivative of this so I can invoke the second condition. Get to here. And when I sub in x equals, when I put in t equals 0, x is equal to 0. So 0 is equal to 0, 0. So sine of 0 is 0, so this whole piece disappears. Cos of 0 is 1, and we can figure out that C1 is C1 has to be 0 as well. So that means our general solution, since C1 is equal to 0, our general solution is just minus 0.05 cosine root. So all simple harmonic motion questions will be of that sort. But what's the problem with simple harmonic motion? Well, even if I take my little model here, I can see that eventually the mass stops moving. We don't have friction, in other words. In our simple harmonic motion, we don't have friction. We got to fix that. We got to add friction. Simple harmonic motion gives us a sine curve, essentially, a shifted sine curve, if I think about it like this is my general answer, that goes on forever with a period of 2 pi divided by that imaginary part of the eigenvalue. So we got to add friction to the model.